And then the signals, like how should we, what's the easiest way to describe the signals? Is it like a true kind of electrical charge? Is it like a kind of a waveform?
Yeah.
How should we think about it?
You can think of every neuron in the brain as like a very small electrical eel. It undergoes a event called an action potential where it changes its voltage relative to the surrounding brain fluid for about a millisecond. And there's a quick spike in its voltage and then a return to baseline. And so if you are in the vicinity of the neuron, just like if you're nearby an electric eel, you can get shocked. If you're in the vicinity of a neuron, you can see that it's fired an action potential because the electric field surrounding the neuron changes. But also, like an electric eel, if an electric eel is shocking something in the Amazon River and you are on vacation in Florida, like you're safe. There's a distance effect, and so practically, if you're more than 1/10 of a millimeter away from a neuron, you won't be able to see the change in its electric field compared to all of its neighbors.
And is it as simple as positive, negative charges? Should we think of it as like zeros and ones from
It's
a coding
saltwater.
perspective?
Yeah, on the outside, it's just salt water. It's just sodiums and potassiums and chlorides moving around. From a coding perspective, yeah, you can think of it as a 0 or a 1. A neuron is either firing an action potential or not firing an action potential. And so in our case, there was an interest in being able to pull down action potentials, these single cell signals that I was describing, these electrical pulses from single neurons, to be able to record those kinds of signals from 10,000, 100,000, or even 1 million neurons simultaneously in a completely implantable system. So one of the things that we came up with that was very cool was a method of actually doing signal processing in an analog circuit before we digitize. And so we took some math that normally is used in the digital domain called principal component analysis, and we realized that we could instantiate it in an analog circuit that could be replicated across, thousands of channels, and do this kind of signal extraction process on the raw data even before we digitize, so that instead of having to digitize the entire signal, we could just digitize a very small snippet in time that had been filtered in the correct way. All you really need to know if you have an electrode surrounded by a few cells is, has a spike occurred? And if so, which of the 1 to 4 cells made it? And so you can see it starts to get very, very compressible.
And so in terms of what the methodology of essentially analyzing it in an analog fashion, and then picking out from there the relevant components essentially that you wanted to convert to digital.
What we've basically done is we've built analog filters that you can pass a spike waveform through the analog filters, and essentially, depending on how similar they are to the filters, they'll pass through more or less easily.
And it's all happening inside of the brain, is what you're
all happening
in terms of
inside
what you're
of a
doing.
little chip inside of the brain, and it can extract features from those waveforms. And then, so one of the filter sets is just optimized to tell whether or not a spike has occurred, and then the other two are essentially trying to pull out a little bit of extra information. So if by chance there are 2 neurons that are being recorded by the same electrode, you have just enough marginal information that you can tell which neuron made the signal.
And is there an analogy, meaning has this particular problem, do you view it as a novel solution, meaning something you quote unquote invented, or was there analogous problems maybe in other sectors or industries that you
This particular way we did it was pretty innovative, but the general concept of what's called compressive sensing, which is knowing what you're looking for and then sort of providing compression and sensing the event at the same time, that exists in other places. And it tends to exist where the signal that you're interested in is inherently compressible and you have a really good model for the statistics of the signal. that allow you to compress it.
Got it.
It's only when you start building the really like DARPA crazy systems that it requires this kind of like real-time parsing out of information. But if you do it, if you're doing that right, you're only throwing away the information that you don't care about.
And how do you determine that before it's converted?
Well, one of the things you can do, which is what we can do right now, is if you're recording the raw signal at full, like essentially like full frame, and then you're also doing the same measurement in the compressed sensing, you can record essentially epochs, in both modes, and then offline ask, hey, how did my performance suffer on the same task with the same neurons when I did it in the raw mode or in the compressed mode?
Got it. So you're actually, if it's like a repetitive type task, you're training it essentially based upon like a feedback loop.
Yeah.
Okay.
You can also simulate the kind of compression that we're doing if you've recorded the full amount of data, and then compare it in that way too. And so that's something we've done. So yeah, you have to throw a little bit of data away, which means you may throw a little bit of performance away. But if it allows you to get to 10,000 or 100,000 channels being recorded simultaneously in the brain, then that's what you gain in channels more than offsets any kind of marginal loss on a per channel basis.